will be Gordana Tdorov from Northeastern University, and she'll speak about higher Auslander algebras. And I just remind you, right after the talk, we'll have the photo of the conference, so stick around.
Okay, thank you. Well, thank you very much for inviting me and giving me a chance to talk about this. So it will be about higher Auslander algebras, which is somewhat different than the topics that we had until now. This is mostly work of Emre Sen, and it's joined also with Shijie Zhu and then me. But as I said, large part is him. These are my two students. Okay, so I want to talk about higher Auslander algebras, but first I want to start with kind of a list of what I will be talking. So the first will be classical Auslander algebras. And that I will put a theorem of Auslander, which is used as main motivation for this work. Then the second will be higher Auslander algebras. And that is something that was introduced by Osamu Iyama. And there is a large amount of work by Iyama and other people. I'm not saying just Iyama, but other people as well. Then the third part is a higher Auslander algebras from Dynkin diagrams. This is mostly work of Emre Sen. And then the fourth part is also higher Auslander algebras from higher representation finite. So I'll define these, but it is coming from higher. Usually it will be K, representation finite algebras. And that's also Sen. And then the fifth one will be again higher Auslander algebras, Nakayama. And that is Sen and also Sen, me, and Shijie. So this party here is the joint work of all of us. Okay. So now let me start with kind of classical Auslander algebra, Auslander correspondence. Auslander, okay, so what I meant is algebra, but actually I meant to talk about correspondence. And similarly here, it will be algebras, but there is also correspondence, which I will state. So here is this number one, that's the theorem of Auslander, which says that for artin algebras, there is correspondence between, okay, algebras of finite, representation finite, okay, of representation finite, and algebras which have a nice homological definition of properties, global dimension. So I'll put gamma here and I'll put lambda here and talk about the correspondence. Global dimension of gamma is less than or equal to 2, and that's less than or equal to the dominant dimension of gamma. So this is the theorem of Auslander, which talks about algebras of finite representation type and algebras which have this homological property on global dimension and dominant dimension. Now, these algebras which have this property are actually called Auslander algebras. Of of course, Auslander didn't call them Auslander algebras. I mean, he had theorem this way, right? But everybody now calls them Auslander algebras. Global dimension, of course, everybody knows what it's the standard global dimension. But I think I just want to point out what is dominant dimension. So dominant dimension of gamma is supremum of P such that when you take injective resolution of gamma, so gamma to I0, I1, IT plus 1, and so on. So this is minimal injective resolution. Then these first injectives up to T have to be projective, so supremum of such T. So how far you can, in the injective resolution of gamma, how far do you actually have projective injectives? Okay, so I0, IT are also projective. So these are injective and they're projective. And then for typical Auslander algebra, what it means is that you have gamma, you have I0, I1, and I2, because global dimension is supposed to be less than or equal to 2, but these first two are also projective. So this is the Auslander correspondence, okay? And I just want to describe this correspondence. So first, I'll describe this way. So if you start with lambda of representation finite.
Is there a good example of one of these Auslander algebras?
I could do example. There are many. Okay. Since this is cluster story, and so if you take the Auslander right-hand quiver, so usually in cluster stories, you see Auslander right-hand quivers like for AN, then that's the quiver of Auslander algebra. Maybe okay, let me do, I'll try also to put, so maybe when I put this, it will also tell you something else. Lambda as representation finite. That means that you have finitely many M1 up to Mn. I'm going to write indecomposable lambda modules. And what I mean is complete set of representatives of isomorphism classes of indecomposable. So usually I won't put all of those words, but so I'm just putting this indecomposable lambda modules. Then you take M to be the direct sum of mi's, I from 1 to n, and you take gamma to be the endomorphism algebra of M. And then this is, so this is Auslander's theorem, this is Auslander algebra. So that's why when you look at Auslander right-hand quiver, it is exactly quiver of that algebra. So this is how you go that way. And now how you go the other way, you start with gamma, which is Auslander algebra. Again, Auslander algebra means this global dimension 2, dominant dimension 2. You pick out all the projective injectives, projective, injective, indecomposable. You take your Q to be the direct sum of these QIs, I goes from 1 to n, and you take lambda to be the endomorphism of that Q now over gamma. And then this is going to be finite representation type. So this is, again, this Auslander, the theorem that I stated here this is how you associate from finite representation type to something. Auslander algebra, I mean, this is very functorial. It's a typical functorial thing that works also. Number of indecomposables here is the same as the number of the projective injectives over the Auslander algebra. Okay.
How do you know that there are finitely many of them? Of projective injective given in the standard algebra?
If you have Auslander algebra, you have finitely many projectives, indecomposable projectives, and then among those, you just pick out ones which are projective injective, and you have to have enough of them because you see, being Auslander algebra, you need this you have to have enough of these projective injectives that you can start Auslander algebra this way. Okay.
Sorry, the two ends aren't, right?
Okay. Let me just see. Okay. No, this first is, yeah, they're not the same. These are just, this is, I'm sorry. Usually in my mind, n was the number of injectives. This number here is how many injectives you have over lambda, or how many projectives, or what is the number of vertices, the number of simples. So that's, this number here is all that. Okay, so now I want to talk about the higher version of that. So this will be a theorem of Iyama. So this is now my second part. So it's theorem of Iyama. So there will be, again, correspondence, again, artin algebras. And again, there exists correspondence. And now, let me write here. So here I will have higher Auslander algebras. And the definition, I'm actually going to put a definition right here, call them gamma, is that the global dimension of gamma is less than or equal. I'm going to put k plus 1 because these will be called higher Auslander algebra. So k, which goes with Auslander algebra, is k plus 1 dimension of global dimension and dominant dimension of gamma. So this is clearly a generalization of the Auslander algebra, which was 2, and here is k plus 1. Okay, and now this part here does correspond to something finite, but we don't have any more finite representation type algebra. So it can be infinite representation type algebra. So what we need there is K cluster tilting subcategory. I will define it after that, but you only want finite. So this is where the finiteness now comes. So it's not that the mod lambda is finite, but that mod lambda, so lambda has finite K cluster tilting subcategory. So mod lambda is infinite, but it has this nice, and now I'm going to define what is K cluster tilting subcategory. Okay, and that will correspond to these higher cluster algebras. And then after that, we can also talk how you go from one to the other. Okay, so here's the definition. C inside of mod lambda is K cluster tilting subcategory. Okay, sometimes we just say higher cluster tilting subcategory, and when we know precisely which number it is, then we put K. Okay, if there are two conditions. The first condition is that C consists precisely of X such that Xi of X and C is 0 for all I between 1 and K minus 1. And actually, that is equivalent to also putting x the other way being 0. So I'm just going to write here, even though it's enough to just do one of them, since it's equivalent. And the second part is that C is functorially finite. Now, functorially finite, I'm not going to define completely, but it's a generalization of finite, and it just means that every object has a left approximation by C and has right approximation. Every module has approximations by C one way and the other, just like projective covers and injective envelopes. The only thing is that it's done with C. Okay, so that's the functorially finite. So functorially finite is not necessarily finite, but all finite are functorially finite. Okay, so that is a K-cluster tilting. So there's the condition on X being 0 up to K minus 1, and it has to be functorially finite. And actually, in most examples that we do, it will be finite. And I also need definition here of algebra K finite representation type algebra lambda. That means it has two conditions. One is that there exists K cluster, there exists finite K cluster tilting subcategory, and the second condition is that the global dimension of lambda is actually K. Then algebra is called K finite representation type. So it's not necessarily finite representation type, but it has to have this thing inside which is finite. Okay. And then, so that is the correspondence. And now there's this nice proposition which is actually useful for computing. It's Iyama. Okay, so lambda is K representation finite if and only if tau K, I will define what is tau K, that is higher Auslander right-hand translation, tau K of d lambda, meaning of injectives, a tau K orbit, okay, orbit of d lambda is finite. And actually that, and that is also equivalent. Okay, I'll just stop at that. And global dimension of lambda is K. Okay, so what happens is that quite often, in order to find this cluster tilting subcategory, it's enough to find this tau K orbit of injective. So you're just taking, oh yeah, I didn't define. Here's the definition of tau K. Definition tau K is tau of omega K minus 1. So omega K minus 1 is just the syzygy. And tau is the classical Auslander right-hand translation. Yeah.
I have a question about the definition of that. When you say xi and xc, you're using the category to define the category, or you're trying to define C, right?
Yeah, I'm defining C. Yeah.
So
C consists, so it's kind of maximal subcategory which has that property, right?
Oh, so that means that for all objects in C.
Yeah, that's why I underlined C, meaning put the whole for anything in C. Okay. Yes.
And then we're taking the full subcategory of these objects, is that right? So we take all of the errors between subjects?
In which part are you asking?
Also in the definition of the cluster tilting subcategory.
It costs it,
Yeah.
C is full. I should have, I thought I'll save some time, but I think I didn't. Yeah, it is full subcategory. Everything from on all other boards, when I say it will be full, even if I forget to say. Okay, thank you.
Also, Can you say some words as to why it's called a tilting subcategory? I usually think of tilting as something that translates between two module categories.
Well, tilting is, you don't have X, right? That is how originally tilting modules and so. Now, calling it cluster tilting, actually it was, Iyama used to call differently. I don't remember exactly what he called. And then it was Idun Reiten and Keller who decided that the good words would be cluster tilting, okay? Because it is kind of similar to, cluster tilting objects in the cluster category, okay? And actually some of the examples that I'll talk later will be exactly, okay. Okay. Now, any other questions? Okay, Tau is the classical Auslander-Reiten translation, but which was actually defined. I like to mention that originally it was dual of the transpose. So in original papers of Auslander and Reiten, it was duality composed with the transpose, the two functors combined. So I guess I originally worked like that, but then later they started to call it Tau. Okay, so now I want to talk about this correspondence. Just as I said here, I want to talk about the correspondence. I didn't put word correspondence. Okay, so first this way will be kind of clear. I start with lambda, which has a C finite cluster tilting, and I will say K finite. Oh, it has K, yeah. It has K cluster tilting, which happens to be also finite, okay? So I start with that, and then of course, if it is finite, it's the typical, you take M1 up to Mn, and these are indecomposables in C. You take the endomorphism, some of them, Mi, and you take the gamma to be the endomorphism of that M. Okay, so these are all indecomposable, put them together. Okay. And now the point is that because you're starting with this C, which is K cluster tilting algebra, then gamma will be K Auslander algebra, meaning that global dimension of gamma will be less than or equal to K plus 1, and dominant it will be bound by dominant dimension. Okay. Now for the other part, is there anywhere watchers?
12:05. 12:05.
So 5, and I go until
20 minutes. You have 20 more minutes.
I have to, oh, okay. So now I'll start with the gamma, this K Auslander algebra. And the first step is again the same. Take Q to be the sum of projective injectives, so that still works the same. Injectives. And now comes the interesting part when you take lambda to be endomorphism of Q over gamma. Now there are two possibilities. Lambda might be a finite global dimension, or it might have infinite global dimension. So this is where one has to be a bit careful. So two cases, global dimension of lambda is finite. And in that case, it will be, there exists unique CK cluster tilting subcategory, which will actually be, you can take it as a module. There exists unique CK cluster tilting and finite. Okay, so if you start with K Auslander algebra, take the endomorphism of projective injectives, you get the algebra. If the algebra that you get has finite global dimension, then there is a unique such a cluster tilting subcategory, which is in addition finite. So this is where the correspondence goes, which is finite, okay? And according to this proposition, you can actually compute it as tau k orbit of the injective. So you just get the injectives and compute tau k orbits and you have it, okay? So this is, in this case, this is k finite representation type. And the other possibility is that the global dimension of lambda is infinite, which is not now bringing me to k finite representation type, it's infinite. And then you may have several possible, k cluster tilting subcategories. And this is where Emre Sen, he wrote in Nakayama's, he was describing Nakayama, several of possible cluster tilting subcategories, okay? Now, the rest of the talk, I will concentrate on k finite representation type. So my 3, 4, and 5 will all be, so these 3, 4, 5 will all be finite representation type. So they'll be all finite global dimension, okay? So now, k finite representation type in general, there is no good, or it's hard to give classification of k finite representation type. So this is just a remark. Classification of k finite representation is hard even for well-known classes of algebras. So I just want to mention what I know so far that is. So first, Iyama has for k finite representation type of A type. So he starts with representation of A like the Dinkin quiver A, and then you construct complicated and complicated algebra. So he has for this. Then there is another paper by Iyama and Hershend, and it is for cuts of pre-projective algebras. And then there is Ringel for Nakayama with just coming out of the quiver AN with 0 relations. Then, then there's another paper, Madsen, Marcinsic, and Zai. It is for Nakayama of defect 1. And now this STZ, so 3 of us, we have for all Nakayama. But again, I mean, Nakayamas are considered to be like relatively simple class of algebras, but as you can see, all these people worked on special kinds of Nakayama, And so this here we have for cyclic, we already wrote, and for the linear, we are writing. We have the results, but we are writing now. So now I want to, the idea of how to construct k finite representation type is first get higher Auslander algebra, then find projective injectives, and then take the endomorphism of Q over lambda, gamma, okay? So that is, this is why I'm talking so much about higher Auslander algebras, because first, in order to get higher K finite representation, first we try to get higher Auslander algebras, because higher Auslander algebras are kind of defined homologically. So we construct higher algebras which have proper dominant and global dimension, and then describe the injectives, and then take endomorphism, and then get algebras like that. Okay, so that is towards this part here. Okay, and now I'm going to type case 3. So case 3 are higher Auslander algebras which are coming from Dynkin diagrams. So again, this is the work of Sen. So he starts with lambda, hereditary, of representation finite. And that means that lambda is isomorphic to the path algebra KQ, where Q is Dynkin. This is the Gabriel's theorem, and so Dynkin. Okay, so with that, and then the next thing is, once you have that, you can look at the derived category of mod lambda. So this is derived category. Now, this derived category will be union of mod lambda, all the shifts, where J is in Z. Now, this is true because lambda is hereditary. So if lambda is hereditary, everything in the derived category, all indecomposable things are stocks. So stock complexes. So that's why it will you just take and shift all the modules. And so it will look like that. You'll have mod lambda, and then shift, and so on. And now at that point, Emre defined CK, so this is the subcategory. It will be full subcategory, which will be where the objects will be given inside of mod lambda, but only J, but only shift J goes from 0 to K. So it will be just start only from the modules and go to the kth shift. So this is now the subcategory, full subcategory of the derived category, and then define gamma K to be the, okay, now again, you have to take all the modules. So you take M to be equal to the sum of the sum. So you take all mi's in mod lambda. So I goes from 1 to n. I'm assuming that lambda is finite representation type. And then you take J goes from 0 to K. So here's it's a module. Okay, not module, sorry. It's a object in the derived category. It's a finite, yeah. And then you take a gamma K to be the endomorphism of that M over the derived category. And then the theorem is that gamma K is higher Auslander algebra, Auslander with global dimension of gamma K is, so we started global, because of this K, it will be 3K plus 2 and dominant dimension like that. So this is a way of constructing higher Auslander algebras, which have higher homological properties. Okay, so that is one, that's in 3. And how many minutes? Do I have any minutes?
10.
Huh?
10.
Oh, I have, oh, good. Okay. Okay, so now let me tell you for 4. So here 4 will be, okay, so you said I have 10. Okay, okay, so the 4 is this one. So I want to start with the algebra, which is of hierarchy representation. So I'm starting with lambda. This is again Sen. I really like this work that he did, so I decided to talk about, okay. So I'm starting with lambda, which is M. I'm going to use now M, finite representation type. And from that, construct many new higher representation finite algebras, okay? So you see here I construct 3k plus 2, okay? But this will construct many more, okay? So I start with M finite representation type. If it is finite representation type, then it has cluster category M finite cluster tilting. And okay, I'll hold it. Okay, and then now you take C M Z. Okay, so you take also shifts of the modules in C. So C has modules in this cluster tilting. There are finitely many of them. And then you take all, not ordinary shifts, but M shifts of those. Okay, now this is actually known to be M plus 2 angulated subcategory. It is by Geis, Keller, and Opperman. And now in here, Emre again takes CK to be equal to C, and you union, I'm sorry, I'm holding this, I guess this is, okay. Okay, so CK will be union, again, of just K first thing. So it will be union of C MJ, where J goes from 0 to K. So this is like the way it was derived category. You have all shifts, and you take here just shifts between 0 and K, but only M shifts of that. Okay, so that's CK. Construct appropriate module, which is the direct sum of MIs, and then shifts MJs. I goes from 1 to N, and J goes from 0 to K, and take a gamma K to be endomorphism M in here, or I can write in the derived category. And then again, theorem is that now gamma K is higher Auslander algebra, Auslander, and the global dimension of gamma K is equal to M plus 2 times K plus M plus 1, and that is dominant dimension of gamma K. So this again creates higher Auslander algebras of now larger and larger global dimension, global and dominant dimension. And if you take endomorphism, if you take sigma K to be the endomorphism of the projective injectives in gamma K, then you get M plus 2 K plus M finite, representation finite. So this again creates many new representation finite algebras. And do I have 2 more? How many?
2, 3 more.
2? Okay, then the last one will be, okay. I guess it will be easier to write here. So this is 5. Okay. Okay, so now I want to start with lambda Nakayama. And there's linear Nakayama and cyclic Nakayama. Okay, so it is KQ mod I, so it's a quotient of a path algebra where Q is either linear or cyclic. Okay, so this is Nakayama, and now this will be a different construction for new higher Auslander algebras. Okay, so you start with Nakayama, and then there are two things that I need to talk. So there's epsilon construction, which is essentially creating epsilon lambda. I am not going to describe it. It's endomorphism algebra of some really nice modules. But the theorem is that the global dimension of epsilon lambda is equal to the global dimension of lambda minus 2, and the same for dominant dimension epsilon lambda is also dominant dimension. So this is the old result of Sen. So what we do now, we do reverse of epsilon construction, and we have the theorem. So I'll state two theorems and the corollary, and that's it. Okay, so the theorem is given a Nakayama, there exist countably many Nakayama algebras B such that epsilon of B is equal to A. So that says that there are countably many algebras which have higher global dimension and higher dominant dimension. So that's part A. Part B is there exists unique algebra B such that epsilon of B is A, isomorphic to A, and defect of B is equal to the defect of A. And part C is that if A is higher Auslander, higher K Auslander, then B in here is K plus 2 Auslander. So this constructs higher and higher Auslander algebras. And the corollary is that this theorem gives description or construction of all higher Auslander Nakayama algebras. So that's the third process of getting higher Auslander algebras, and for Nakayama, this characterizes all of them. Okay, and I think I.
Are there any questions?
Yeah, so when you say that there exist countably many B, so that epsilon B is A, do we know what they all are?
Yeah, we have precise description, exactly. Description, yeah. It's very precise. Oh, the effect, okay. The effect of algebra is the number of injective but not projective modules. No. Oh, I'm sorry. I should have said this. No, it is the number of these injectives which are not projective.
There's a question in the chat.
If A is a higher Auslander algebra constructed as in part 3, has anyone looked at the tilting modules which lie in the K cluster tilting subcategory?
In part 3, yes. I just skipped it for the time. Where is my 3? 2. Oh, 3. Yeah, here's the 3, right? This is the one. Okay. So the cluster tilting. Okay, so first of all, I did, yeah, here's 3. Okay, so I didn't describe sigma k, right? So so this is higher Auslander, okay? Then sigma k is endomorphism of the projective injectives over gamma, and it is also isomorphic to the endomorphism of dual of lambda plus the shifts of m I j is from 1 to k. So it's endomorphisms from this one before and this. Okay, and these will define the injectives, and then you need to find the tau 3k plus 2 of d sigma k. So here is precise, there is a very precise description of the injectives over, right? And then you have to take this tau using this property here. That is how you compute the subcategory. Okay. Did whoever asked? Oh, okay. Yeah. So it is this higher. It's the higher Auslander-Reiten orbit of the injectives over sigma k. And sigma k and everything is precisely described. Actually, in my notes, I wrote my precise description, but then when I timed it, I realized that I should skip all of that.
Are there any more questions? Okay, if not, thank you for the great end. And now I think there's the photo.